Welcome my dear learners for this course on mechanical vibrations. In this module 2 we were discussing on forced vibration system analysis and vibration measuring instruments. So far we have started the discussion on numerical problems on forced vibration analysis. In our previous lecture I have recollected the formulas which we have derived so far and also solved 3 numerical problems on forced vibration systems subjected for harmonic excitation. Let us continue from the point where we have stopped in our previous lecture. Moving ahead, in today's lecture I am going to address numerical problems on rotating and reciprocating unbalance. Hope you people have watched our previous lecture and understood the formulas what we have derived so far. And recollecting the formulas which we have discussed in our previous lecture, let us address our problem number 4, 5, 6 in our today's lecture. I am giving the solution for the question bank which I have attached to the link given in the description. Kindly click on the link given in the description below this video to get access to the question bank. For that question bank I will be discussing the solution in this lecture series. Moving ahead, the problem number 4 of our discussion states that an electric motor is supported on a spring and a dashpot. The spring has the stiffness of 6400 Newton per meter and the dashpot offers resistance of 500 Newton at 4 meters per second. The unbalanced mass 0.5 kg rotates at 5 cm radius and the total mass of vibratory system is 20 kg. The motor runs at 400 rpm. Determine damping factor, amplitude of vibration and phase angle, resonant speed and resonant amplitude, and force exerted by the spring and dashpot on the motor. Now if I list out the data given for our problem number 4, what we have: an electric motor is supported on a spring and a dashpot. The spring has a stiffness of 6400 Newton per meter. The stiffness of the spring is given, which is 6400 Newton per meter, and the dashpot offers a resistance of 500 Newton. So is given the details of dashpot. Coming for the dashpot, the force exerted by the dashpot is 500 Newton at 4 meters per second. At 4 meters per second, the unbalanced mass is denoted by m0. You people already know this, which is 0.5 kg, rotates at 5 centimeter radius. It is nothing but eccentricity E, which is 5 centimeter, which means 0.05 meters. And the total mass of vibratory system, that is m, which is 20 kg. The motor runs at 400 rpm. The speed of motor is given, which is 400 rpm. Determine A, damping factor zeta, B, amplitude of vibration and phase angle. Amplitude of vibration and phase angle phi. The resonant speed, C, the resonant speed, that is n max. It is not max, it is at resonance. Sorry, resonant speed or critical speed he is asking. Let us take it as n resonance and resonant amplitude. The condition at which excitation frequency matches with the natural frequency is termed as resonance. At resonance, the amplitude of vibration will be maximum. So therefore, resonant amplitude means maximum amplitude, A max. The speed of rotation need not be maximum. It is a condition only which natural frequency equals excitation frequency. At that point, we will get only maximum amplitude. It is not maximum speed. Keep that in mind. The speed at which resonance occurs is termed as critical speed. So here what he is asking is critical speed and maximum amplitude. And also D, force exerted by the spring and dashpot on the motor. So F of spring and F of dashpot. So this is the question he is asking. Let us solve this problem. Now let us discuss one by one in detail. As you already know, this is unbalanced setup by rotating mass, because electric motor has rotor in it, so it is the unbalanced setup by rotating mass. From the discussion of rotating and reciprocating unbalance, we know that the amplitude ratio equation is given by A divided by m naught E by m is equal to omega by omega n whole square divided by square root of 1 minus omega by omega n whole square plus 2 zeta omega by omega n whole square. Recollect the formula of amplitude ratio for rotating and reciprocating unbalance. And also we have one more formula for phase difference. The phase difference tan phi is equal to 2 zeta omega by omega n divided by 1 minus omega by omega n whole square. So we have only two formulas for rotating and reciprocating unbalance, and rest of the things are basics. Let us recollect and solve this problem. Since I know dashpot force and velocity, I can find the damping coefficient. So what is the general formula for damping coefficient? Damping coefficient is given by damping force per unit velocity, right? So therefore, how much is damping coefficient? Dashpot offers a force of 500 Newton at a velocity of 4 meter per second. So hence damping coefficient for this problem will become 500 by 4, which is nothing but 125 Newton second per meter. Now we know the general formula for critical damping. Critical damping coefficient Cc is given by 2 root mk or 2m omega n. Let me use 2 root mk. If I use this formula, we have 2 into root of mass is 20 kg into stiffness is 6400 Newton per meter. Hence critical damping coefficient for this problem is 715.54 Newton second per meter. Now we can find the value of zeta, correct? Now I can find the value of zeta. The formula for zeta is C by Cc. So if I substitute and solve, C is 125 and Cc is 715.54. So damping factor or damping ratio for this problem is 0.175. So we found out the damping factor. Now he is asking to find amplitude and phase angle. So what is the formula for amplitude ratio for rotating and reciprocating unbalance? Amplitude ratio A divided by m naught E by m. M naught E by m is equal to omega by omega n whole square divided by square root of 1 minus omega by omega n whole square plus 2 zeta omega by omega n whole square, correct? So this is the formula which we have derived for rotating and reciprocating unbalance. Now we know all the values, right, except natural frequency. So we know the speed of rotation of the motor, which is 400 rpm. Hence I can find the value of omega as 2 pi n by 60, which will turn out to be 2 into pi into n is 400 divided by 60, which will gives us the value as 41.888 radians per second, whereas omega n is already known, root k by m or root g by delta. So your static deflection is not known, hence I am using root k by m. What I am going to get, the value of k is 6400 Newton per meter, value of mass is 20 kg, hence natural frequency of this vibrating system is turning out to be 17.889 radians per second. Now substituting the values, I can find the value of amplitude A. Amplitude A will become m naught is 0.5 into eccentricity is 0.05 divided by mass is 20 kg into omega by omega n. So how much the ratio we are going to get? The ratio omega by omega n will be 41.888 divided by 17.889. The ratio is turning out to be 2.34. So it is 2.34 square divided by root of 1 minus 2.34 square whole square plus 2 into how much is zeta? 0.175 into omega by omega n is 2.34 whole square under the root. So hence the amplitude of vibration will become 0.5 into 0.05 divided by 20 multiplied by 2.34 square divided by root of 1 minus 2.34 square whole square plus 2 into 0.175 into 2.34 whole square. So if I solve, I will get the amplitude of vibration as 1.504 into 10 to the power of minus 3 meters. So which is nothing but 0.1504 centimeters. We have calculated the amplitude. That is question B what he has asked. In that itself he is asking the phase difference. We know that phase difference phi is given by tan inverse of 2 zeta omega by omega n divided by 1 minus omega by omega n whole square. This you people already know. So if I substitute and solve, how much I will get? Phi is equal to tan inverse of 2 into zeta is 0.175 into omega by omega n is 2.34 divided by 1 minus 2.34 square. So if I solve, I will get the answer for phi as minus 10.37 degrees, or we know that tan of 180 plus theta is tan theta. So hence I can take this as tan of 180 plus of minus 10.37. So how much I will get if I add 180 for this? I will get 169.63, or the angle is 169.63 degrees, because tan of 180 plus theta is tan theta, third quadrant. So add 180 for this, 180 minus 10.37 it will become, it is 169.63 degrees. So if you take the value for this, so how much you will get? You get the value as minus 0.183 for 169.63, and for minus 10.37 also you are going to get the same answer, minus 0.183. You can check. Next, moving for C. He is asking resonant speed, that is critical speed. He is asking the speed at which resonance occurs. So for resonance, for resonance you people already know omega should be equal to omega n. Hence what will be the value of omega? Omega will become omega n, that is 17.889. Hence we know that omega is equal to 2 pi n by 60, right? So it is 2 pi n resonance by 60 is equal to 17.889. Hence the value of speed at resonance speed at resonance will become how much? 17.889 into 60 divided by 2 into pi, which is 170.827. 170.827 RPM is the resonant speed. And resonant amplitude, coming for resonant amplitude, we know that, so at resonance omega is equal to omega n, right? So it will become 1. 1 minus 1 is 0. This will get vanished. Here I substitute 1. So I have only 2 zeta whole square. Square and square root will get cancelled. Omega by omega n is 1. So I will get only 1 divided by 2 zeta. 1 by 2 zeta is what I will get at resonance. So therefore at resonance what will be the equation? A max divided by m naught E by m will be equal to 1 by 2 zeta. Correct? Will be equal to 1 by 2 zeta at resonance. Now we know all the values. If I substitute and solve, what am I going to get for A max? A max will become m naught E by m. We know all the values. Substitute and solve. 0.5 into 0.05 divided by 20 whole divided by 2 into zeta. How much is zeta? 0.175. So therefore at resonance the amplitude of vibration will be maximum, which is nothing but 0.5 into 0.05 divided by 20 divided by 2 into 0.175. So I am getting the answer as 0.357 centimeters. 0.357 centimeters. It is 3.57 into 10 to the power of minus 3 meters. I can write it as 0.357 centimeters. Done. So moving for the last one, what he has asked, force exerted by spring. So spring force is given by stiffness times the amplitude of vibration. Correct? Because stiffness is defined as force per deflection. How much is the deflection? Deflection is 0.1504 centimeters. So stiffness times the deflection will give us spring force. So if I substitute and solve, I will get the spring force as K is 6400. Let me substitute and solve. It is 6400 into amplitude of vibration is turning out to be 1.504 into 10 to the power of minus 3. So how much I am going to get? It is 6400 into 1.504 into 10 to the power of minus 3, which is nothing but 9.6256. 9.6256 newtons. 9.6256 newtons is the spring force. And we have damping force. Damping force is given by C into x dot. So what is the value of velocity, maximum velocity? C into omega A. Correct? Maximum velocity is omega A, maximum acceleration is omega square A, whereas amplitude is here. Why I am not taking A max? A max is only at resonance, but we are calculating the spring force and damping force when the speed is 400 rpm. Kindly make a note. So the general formula for damping force is C omega A. Kindly keep that in mind. Now if I substitute and solve, how much I am going to get? The value of C is calculated as 125 into omega is at 400 rpm, omega is 41.888 into A. A is again 0.1504 into 10 to the power of minus 2 I should take centimeters. So I will get the answer as 7.8749. Let me substitute and solve in order to avoid confusion. C is 125, omega is 41.888 into A is 1.504 into 10 to the power of minus 3. So I'll get the answer as 7.875 Newton. So force exerted by spring is 9.65 to 6256 Newtons, whereas damping force is 7.875 Newtons. If I want, I can also find resultant force. Let me find resultant force also. So resultant force is nothing but root of force of spring plus force of spring square plus force of dashpot square. So how much is the resultant force? It is root of 9.6256 square plus 7.875 square. It is 12.44 Newtons. 12.44 Newtons. So this is the solution for problem number 4. Now let us quickly move ahead to solve problem number 5. So if I move ahead for problem number 5, problem number 5 states that a single cylinder vertical petrol engine of total mass 320 kg is mounted upon a steel chassis and causes a vertical deflection of 2 mm. The reciprocating parts of the engine have a mass of 24 kg and move through a vertical stroke of 150 mm. With simple harmonic motion, a dashpot attached to the system offers a resistance of 490 newtons at a velocity of 0.3 meters per second. Determine the speed of the driving shaft at resonance and the amplitude of steady state vibration when the driving shaft of the engine rotates at 480 rpm. Let us list out the data given for our problem number 5. If you carefully observe, it is a single cylinder vertical petrol engine. So it is a reciprocating unbalance. It is a problem on reciprocating unbalance. It is a problem on reciprocating unbalance. The total mass of the engine is specified. The total mass of the petrol engine is turning out to be 320 kgs. And we have the static deflection delta is 2 millimeters, 2 mm. The reciprocating parts of the engine have a mass. So unbalanced mass, reciprocating unbalanced mass m naught is 24 kg and move through the vertical stroke. He has given the stroke. Stroke is 150 millimeters. With the simple harmonic motion, the dashpot attached. So is given the details of dashpot. Dashpot exerts a force of 490 Newton at 0.3 meters per second. Determine A. The speed of the driving shaft at resonance, that is critical speed, N at resonance, and B, the amplitude of steady state vibration. Amplitude of steady state vibration when the driving shaft of the engine rotates at when N is 480 rpm. So this is the question what he is asking. Now if we quickly move on for the solution of this problem, as he has given the value of static deflection, let me determine the natural frequency omega n is equal to root k by m or root g by delta. Here stiffness is not specified, instead of which he has specified the static deflection. Hence I can use the formula omega n is equal to square root of g by delta. So how much delta will be? Delta will be 2 into 10 to the power of minus 3 meters. Now if I substitute, I will get square root of 9.81 divided by 2 into 10 to the power of minus 3. Natural frequency for this problem is 70.036 radians per second. 70.036 radians per second. As we already discussed when our discussion on rotating and reciprocating unbalance, the formulas what we have derived for rotating unbalance holds good for reciprocating unbalance also, right? So therefore I can use the same formulas what we have for rotating unbalance to solve problems on reciprocating unbalance. Now the question is that he has given the stroke, but he has not given the eccentricity, because I want eccentricity, right? Without that I cannot solve for amplitude. Anyhow I can find resonance speed with natural frequency itself. That I can do. Let me finish that off. At resonance, what is the condition at resonance? At resonance, omega is equal to omega n, hence omega should be equal to 70.036. We know that 2 pi n resonance by 60 will be equal to 70.036. Hence the speed at resonance will be how much? How much is the resonance speed? 70.036 into 60 divided by 2 into pi, which is turning out to be 668.79. 668.79 RPM. 668.79 RPM is the resonant speed. Done. Now I want to find the amplitude. Now moving to find the amplitude of vibration. We know n, hence I can find the value of omega. So we know omega n, which is 70.036, whereas omega is 2 pi, n is how much? 480, 2 pi n by 60. Hence omega can also be found out as 2 into pi into 480 by 60, which is 50.265. 50.265 radians per second. Now I want to find the eccentricity E, correct, for which he has given the value of stroke. So now if I carefully observe a petrol engine, let us have the bottom dead center and the top dead center. Let us say this is top dead center. This is attached through a connecting rod, and we have the engine cylinder crank like this. So now we have the connection like this. Now if you carefully observe, one stroke is equal to how much? One distance travelled from bottom dead center to top dead center, correct? From bottom dead center to top dead center, how much will the rotation of the crank? How much is the crank angle? Crank angle will be how much? For one stroke, from TDC to BDC, or from BDC to TDC, for one forward stroke, how much will be the rotation of the crank is my question. How much is the crank angle? Crank angle will be bottom to top, which means 180 degrees, correct? One forward stroke will have 180 degrees of crank rotation. So therefore, since the travels is 180 degrees from BDC to TDC, from bottom dead center to top dead center, the angle traced must be 180 degrees, correct? Now for 180 degrees, so this will be the tracing, this will be the angle 180 degrees, correct? So for 180 degrees he has given the length is how much? 150 millimeters. 150 millimeters will become what? Diameter, correct? 150 millimeters will become what? From here to here it is 150 mm, means how much is that? Which is nothing but diameter. But what is eccentricity? Eccentricity is radius. Eccentricity is radius, whereas stroke is diameter. Hence eccentricity will be what? Or else I can write like this, no? Stroke is equal to 2 times the eccentricity. Hope you followed. Now I can find the value of eccentricity. So how much is eccentricity? So this is The catch for this problem, stroke is 150 mm, that is 0.15 divided by 2, which is 0.075. So 0.15 by 2 meters, which is nothing but 0.075 meters. Now we know all the values. So if I substitute and solve, I will get the solution for amplitude. Right. So what is the formula for amplitude? So this formula for amplitude is already known for us. Amplitude A is equal to m naught E by m into omega by omega n whole square divided by square root of 1 minus omega by omega n whole square plus 2 zeta omega by omega n whole square. Now if I substitute all the values, I am going to get the answer, but we have not yet calculated the value of zeta. Zeta is C by Cc. So as given the information about dash pot, hence I can find the value of C as dash pot force divided by dash pot velocity. So dash pot force is 490, dash pot velocity is 0.3, hence the value of C will be 490 by 0.3. How much is that? It is 1633.33 Newton second per meter. Now we can find the value of Cc. Cc is, let me use 2m omega n directly because I know omega n. So 2 into mass is 320 into omega n is 70.036. So Cc will be 44,823 Newton second per meter. So hence I can find the value of zeta. Zeta will be C by Cc. C is 1633.33 divided by Cc is 44,823. So I'll get the value of zeta as 0.036. 0.036 is the value of zeta, C by Cc. And how much is omega by omega n? It will be also useful for us. The ratio of omega by omega n. Omega is 50.265 divided by omega n is 70.036. 70.036 radians per second. The ratio will be 0.7177. 0.7177. Now we know all the values. We know the value of zeta, we know the value of omega by omega n, we know m naught E by m. So we know all the values. If I substitute and solve, I will get the value of amplitude of vibration. How much is amplitude of vibration? M naught E by m, that is 24 into eccentricity is 0.075 divided by m. M is turning out to be 320 kg into omega by omega n is 0.7177 square divided by square root of 1 minus 0.7177 square whole square plus 2 into zeta is 0.036 into omega by omega n is 0.7177 whole square. So if I solve, I will get the value of amplitude as 5.94 millimeters. 5.94 mm is the amplitude of vibration, which means they are providing very good damping for this system. So this is the solution for problem number 5 of our discussion on forced vibrations. Let me pause this video for a while so that you people can copy it down. Later we will solve problem number 6. Now moving ahead for problem number 6, we are discussing the solution for the question bank which I have attached through the link given in the description. Kindly click on the link given in the description to get access to the question bank. For that question bank, we are discussing the solution in this lecture series. Now moving ahead for question number 6 of our discussion on forced vibration analysis. The question number 6 states that an industrial machine of mass 455 kg is supported on a spring with a static deflection of 0.5 centimeters. If the machine has a rotating unbalance of 2.5 kg meter, determine the force transmitted at 1200 rpm and the dynamic amplitude at that speed. So if I list out the data given, the problem is on rotating unbalance. He himself has been stated in the question. The problem is based on rotating unbalance. The industrial machine has a mass of 455 kgs, which is supported on a spring with a static deflection. He has given the deflection of the spring, which is 0.5 centimeters. If the machine has a rotating unbalance of 2.5 kg meter, so it is not 2.5 kg. If it is 2.5 kg, then it is m0, that is unbalanced mass. But what he is giving is the product of m0 into E, that is 2.5 kg meter. So kindly make a note of it. He has given the product of m0 into E, which is 2.5 kg meter. Determine the force transmitted. Determine the force transmitted Ft at 1200 rpm. N is 1200 rpm and the dynamic amplitude at that speed. And what is the amplitude at that speed is the question. Now if you carefully observe and read the problem, the industrial machine is supported only with the help of springs. There are no dashpots attached to it. So therefore the force what will be transmitted is only spring force. It is not the sum of spring force and damping force like how we did here. It is not, the resultant force is not the damping force and spring force. It is only spring force for this problem because the machine is supported only on springs. There is no dashpot attached. Let us solve this problem. If I move for solution, let us quickly move for solution of this problem. Since the dashpot is not specified, zeta is 0. It is an undamped system. Now he has given the value of delta. So whenever he has given the value of delta, natural frequency should be calculated with the help of root of g by delta, static deflection. So omega n will become how much? Root of 9.81 divided by static deflection will be 0.5 into 10 to the power of minus 2, which is nothing but 0.005 meters. 0.005 meters. 0.005. Hence the natural frequency will be 44.294 radians per second. So this is the natural frequency. Now he has given the value of speed. So hence I can find excitation frequency omega, which is 2 pi n by 60. Hence omega for this problem will be 2 into pi into speed is 1200 divided by 60, which is turning out to be 125.66 radians per second. So the ratio omega by omega n will be how much? Omega is 125.66 divided by omega n is 44.294, which is 2.837, which is 2.837 is the omega by omega n ratio. Now let me verify omega once again. 2 into pi into 1200 by 60, 40 pi, 125.66, correct. So the calculations are correct. Now moving ahead, I want to know the amplitude, then only I can find the force transmitted. Even though the force transmitted is stiffness times the amplitude. The spring force is Ka, right? I want K and also I want A. Let me calculate K first. If I want to calculate the value of K, so what will be the value of K? We know that omega n is equal to root of K by m. Hence the value of K is omega n square into m. So hence K will be how much? Omega n is 44.294 square into mass is 455. So hence the stiffness of the spring is 8,92,691 Newton per meter. Got it. I got the stiffness. Now I want the value of A, correct? We know that the amplitude A divided by m naught E by m will be equal to omega by omega n whole square divided by 1 minus omega by omega n whole square. This is because of the reason the value of zeta is 0. What I mean to say is that substitute the value of zeta in this formula. If I put zeta is equal to 0, this term will become vanished. Now the square and square root will get cancelled. I left out with this formula. Now the careful observation is that the ratio omega by omega n is greater than 1. So during such cases I am going to get the negative results. So therefore what you should do is that whenever you encounter the case of undamped forced vibration, this is an undamped forced vibration analysis because we don't have dashpot attached. In such situations, when omega by omega n is greater than 1, you should always stop at this point and inspect for undamped forced vibration. For undamped forced vibration, whenever omega by omega n is greater than 1, then you should make this change. Note, since omega by omega n is greater than 1, rewrite the formula like this. It will become A by m naught E by m, which is equal to omega by omega n whole square divided by omega by omega n whole square minus 1. This is how you should write. Otherwise you are going to get the negative results. Now if you substitute and solve, you will get the answer. That is A is equal to m naught E by m. M naught into E is given for us, which is 2.5 by m is 455 kgs into omega by omega n is 2.84 I can take divided by 2.84 square minus 1. So how much is the dynamic amplitude? So dynamic amplitude for this problem is turning out to be 2.5 divided by 455 into 2.84 square divided by 2.84 square minus 1. So how much is that? 6.27 millimeters. 6.27 into 10 to the power of minus 3 meters, which is nothing but 6.27 millimeters. Now I can find what is the dynamic force transmitted. That is dynamic force transmitted is nothing but spring force. Ft, spring force is nothing but K into A. We know the value of K, which is 88,92,691 into A. We know the value of A, we should substitute in meters. It is 6.27 and 10 to the power of minus 3. If I substitute and solve, the dynamic force transmitted will be 5,599 newtons. 5,599 newtons is the dynamic force transmitted, which is nothing but spring force. So this is the solution for problem number 6. So in this lecture we have completed the discussion on numerical problems on rotating and reciprocating unbalance. In our next lecture I will take up numerical problems on support motion. That's all from this lecture. Thank you all.